Hi, this is Professor Fernandez, and this is video 1B in lesson 19. The B here refers to the fact that this is a continuation of the previous video, 1A, 19.1A, on the same topic. So we're talking here about u-substitution as an integration technique. And in this video, we'll work through two examples here from Calculus Simplified. I do recommend that you take a look at that previous video, video 19.1A, if you haven't already. That reviews some of the very basics of the u-substitution technique, and it also reviews a good rule of thumb for what to choose as your u. So I'm going to use all of that in this video. Either way, I'll quickly review it anyhow, but it might be good to take a look at all that in detail in that video. Okay, so let's take a look at this first example here. This is an indefinite integral that is something we might not know how to do initially. So this is one of the ways that you get to use substitution if you're not told that it's what you want to use, as we are in this video. So what would we do here to use substitution? Well, the rule of thumb that I talked about in video 1A was look for a composite function in the integrand. Okay, here's the integrand, and down here is a composite function. And then in that composite function, every composite function has an inner function and an outer function, f of g of x, right? So look for the inner function. In this case, that's 1 plus x squared, and try that as your u. So that's the very first rule of thumb, right? Most of the time this will work, not all the time. We'll talk about that in another video. But let's go through here and let's see if it works in this case. Okay, once you have chosen your u, in u-substitution, you find your differential du, which is just the derivative of u, 2x, times dx. Great. And then your next step is to go back to your integrand and re-express it in terms of u and du. Sometimes this is pretty straightforward to do, like in the first example in the previous video, 19.1a. Other times it takes a little algebraic manipulation, right? So in particular, in the numerator here, we have x dx. Over here, we have x dx, but we have to get rid of the 2. So I will divide by 2 on both sides here to isolate my x dx. And then now I can use that to substitute here for du. And then the denominator I already have in terms of u, because u is 1 plus x squared. So this is just, this whole thing here is u, square root of u, right? And then I'm going to write that as integral du of u to the 1/2, and then convert that even further into u to the minus 1/2 du. Okay, so the first step in u-substitution has worked out. I have converted the integral in terms of x to an integral entirely in terms of u. I've eliminated all the x's. Great. The second step is the integral that I have obtained simpler to do, right? Can I actually do it? At least simpler than the original integral I started off with? The answer is yes, because over here, this is just a power function, so I can apply the integral version of the power rule, which says that you add 1 to the exponent, so negative 1/2 plus 1 is 1/2, and you divide by the result. And then plus c, because we're doing indefinite integrals. And then last step in integration by u-substitution, we have not finished. This is an answer in terms of u. I started off with a problem in terms of x. I have to convert back to u, to x's. How do I do that? Well, my original substitution here, I just take that, plop it in there, and I get 1 plus x squared to the 1/2 divided by 1/2 plus c. So to clean this up a little bit here, what would I end up with? Well, this would be the 1/2 here. Let's see. Just looking through here to make sure. Oh, there's one thing that I missed. Yes, so the 1/2 over here. So x dx, when we replaced it here with the u's, should have put the 1/2 outside here. So there should be a 1/2 there, there should be a 1/2 there, should be a 1/2 there, there should be a 1/2 there, which means, quite nicely, that then this 1/2 and that 1/2 cancel. So there's no denominator over here. Okay, great. So small mistake initially there. And then over here we have 1 plus x squared to the 1/2. That is fine as is, but we might also want to express it in terms of a radical. So square root of 1 plus x squared plus c. Great opportunity to mention what I was going to mention anyhow, which is in every integration problem, at the end, of the problem, when you think you've gotten an answer, like we have over here, it is always a good idea to check your work. How would you do that? Well, this is your capital F of x function, the antiderivative. Differentiate this function, and you should get your original integrand, which is that one. If we had done this here, we would have noticed that we missed that factor of 1/2, right? Because we wouldn't have gotten this exact function. We would have gotten half of it or twice it, however the math works out. Okay, so that's the first example here. So I'm just going to zoom out and clean up the clutter here. So I wouldn't call this a straightforward integration by use substitution example, but it is probably among one of the simpler ones. Let's look at this one. This one is a little harder. And why is it a little harder? Well, we'll see in a minute. It's a little harder because the integrand is simpler, which seems counterintuitive, but the same guiding principle that we talked about earlier will help. So I don't see how to do this integral using one of the formulas or integration results we already know. It's not the integral of like x to the fourth or something, integral version of the power rule. So that's another way you would know to try use substitution. Okay, and then the rule of thumb that I gave earlier kicks in. Find the composite function, here it is. Find the inner function, there it is, and then try that as your u. So u is x plus 1. So let's try that, see what happens. So u is x plus 1. The derivative, the differential du is the derivative of x plus 1, which is 1 times dx. And this is what really, we've now come to the point where you can see sort of why this is a little bit more complicated. Now that we start substituting things back in to convert this into an integral in terms of u, we have to find x plus 1. It's pretty easy, there it is. And we also have to find 1 times dx. For some people, this is a little difficult because there is no 1. I don't see it, right? I see the dx, I don't see the 1. But it's hidden, right? So 1 is right there. So that is my 1 times dx is my du. This is really the only thing that makes this particular example a little more complicated than the one before. Because if you're used to mechanistically saying, I'm going to look for this, and then I'm going to look for exactly this in the integrand, right? This one is hidden. So, it might present a little bit of a problem for you to find it if you can't see it, even though it's not there. So all that being said, let's now then convert this, the 1 dx, as we said, that is literally du, and then u is x plus 1. So this is u, square root of u, and there we go. We're kind of back to where we were before. This is the integral of u to the 1/2 du, except before we were doing the integral of u to the minus 1/2, right? So integral version of the power rule, we add 1. 1/2 plus 1 is 3/2. We divide by that, divided by 3/2, plus c, and then we're dividing by 3/2, which means we're multiplying by 2/3. There we go. And then last step, as usual, we want to convert back to x's. How do we do that? Well, u is x plus 1. So x plus 1 to the 3/2 plus c. And there we go. And then again, as I said, you could check your work by differentiating this function, making sure, verifying that you then obtain square root of x plus 1. And you will indeed. Okay, so I'll zoom out and just mention one last quick thing to end the video. This rule of thumb that we keep talking about, find the composite function and then the inner function, try that as your u. Find the composite function, the inner function, try that as your u. Very useful rule of thumb. I recommend you kind of get more comfortable with that by just doing more examples. It does rely on your ability to spot composite functions and then to spot the inner function of that composite function. So it goes back to some of those skills earlier. But certainly if you are at this point in this course, this is chapter 5 in our book, you've gotten a lot of practice with this. Great, so I'll see you in the next video.